Let's wait a second.
Okay.
There's no feedback with both of these?
Usually I have both of them on. Podium mic handle. Helps with anyone who's driving in to have where you stand.
I guess I'll not go too close to that one.
Yeah.
Yeah, maybe stay a little further back. Hello. Oh, great. We're going to start in... Great. Okay, I'm staying over here. We're going to start in maybe a minute late to see if other people... Or is this everyone? I know it's the last session, so... Thank you all for being here. All right, people still come in. I'll give it 1 minute. So everyone online, hello. Wait, give us 1 minute. Cool. Okay, well, let's get started so we stay on time. All right, so welcome to the final session of this conference. Thank you, everyone, for being here. It's been a long haul. Glad you're here. The first talk we'll have is by Santosh, and it's going to be the first look at JWST MIRI 7.7 micron sources in Cosmos Web. Take it away.
Cool. Okay, people in the back, can you hear me? Okay, cool, thanks. All right, good afternoon, everyone. Thank you all for being here. The last session. We've had some wonderful talks over the last few days, and we've gone from all the way from galaxies to exoplanets. Now we're back to galaxies, I suppose. So I'm Santosh Harish. I'm a postdoc at RIT in Rochester, New York. And today I'm going to be talking about Cosmos Web and the MIRI component of it. So before I get started, I just want to thank the organizers for giving me an opportunity to talk about this wonderful work done in collaboration with the Cosmos team, led by co-PIs, Jehan Kartilap and Caitlin Casey. All right, clicker works. Okay. Okay, now it works. Sorry. So earlier this week, Max sort of introduced the Cosmos Web survey. So just to sort of recap and rekindle that memory. So Cosmos Web is in the Cosmos part of the region on the sky. Why is it so important? Cosmos is one of the most well-studied regions on the sky. It has multi-wavelength rich data set ranging all the way from X-ray to radio. And it has a ton of spectroscopic redshifts, some of which will sort of like be updated and sort of coming up in an upcoming paper by my fellow colleague Ali Ahmad Kostawan at RIT, confirming up to like 160,000 spectroscopic redshifts, up to redshifts of 8. So Cosmos Web, led by Jehan and Caitlin, sort of looks at using JWST in 4 NIRCam filters and 1 MIRI filter, so as shown here. The NIRCam part of it is in blue and the MIRI in orange red. So the NIRCam is contiguous, but the MIRI isn't. So it's roughly 0.5 square degrees in NIRCam and roughly 0.2 square degrees in the 1 MIRI filter. So we had observations taken over like the last few months, think I'll stop using the clicker. Yeah. So there were these 6 visits that were observed initially earlier this year in January, and then subsequently the half of the field, roughly, was observed in this summer, shown in these red arrows. So in total, there were like totally 78 visits, but 4 of those failed due to guide star failures, and they'll be reobserved in the last set of observations later this year or early next year. But one of them was reobserved. Just a quick overview of we use the JWST science calibration pipeline to reduce the data for most part of it. At this point, I just want to pause for a moment and thank everyone here at STSCI and the user community as such for providing this wonderful pipeline, which works like amazing with all the new modifications we are making as we are learning. So media reduction is like nothing new in that sense. Like we feed in the uncalibrated raw data and then eventually come up with the mosaics resampled images. So we use these versions for the 2 different observations, and all of this was done on Candide, thanks to our, it's this supercomputing cluster in IAP Paris, so thanks to our collaborators there. So for the good part of it, unlike in case of NIRCam, we did not have much issues in case of MIRI, except for one issue. So MIRI is, the imager is sort of strongly affected by the instrumental background feature, which is kind of shown in here. So this is one of the visits. So this is before we applied a subtraction of our own, which was custom. So what exactly we did was we took each visit and then masked all these sources out and created what is called as like a master background, and then sort of combined that over multiple visits taken over a defined period of time, and then effectively subtracted that out of the stage 1 rate images, and then eventually rerun stage 2 and stage 3 calibrations. And then we were able to get a pretty nice image devoid of that instrumental background. So we were successful pretty much throughout without any issues. And we feel with the depths that we have achieved, I think it's pretty remarkable. So these are the 6 observations that were sort of published in our overview paper. So this kind of shows the 6 observations, and then and you can just see how remarkable it is in terms of just the number density of sources that over here in comparison to Spitzer. So we followed a pretty tight pattern. So since there was just one filter, so eventually ended up getting a pretty deep exposure in just this one filter, while NIRCam was cycling through the short wavelength and the long wavelength filters. And the depths we achieve is something that's shown on the top right plot over there. So compared to what the ETC said, it's like we achieved almost 3/4 of a magnitude sort of deeper than what was shown in ETC, even with the updated one. So we didn't believe ourselves, but it was pretty amazing. And so this is something consistent across all our visits. So that's the median depth that's reported over there. And like I said, so we have exposures ranging from 2 to 8, since we had that advantage as well. But the median depth across all exposures is roughly 25.7. And this is just the mosaic of like all the 76 visits taken in April, 72, because 4 were skipped. And I've kind of cheated there, but it's like there are like these 3 visits from the January observations also in here. But that just shows like the total area that's covered so far. So that's roughly a little more than half of what we intend to sort of observe over the next, by the end of the completion of the program. And like I said, the median depth is roughly 25.7. And just to show you, so this is what I know people have shown tons of images showing how great JWST has been. It's been pretty spectacular in NIRCam. I just want to show you how spectacular it has been in MIRI. So there you go. So it's pretty remarkable. I know these are like nearby objects, but still, it just blows my mind every time I show this image. So the kind of solution and sort of detail that we are able to get with MIRI at this wavelength is just remarkable. So yeah, there's so much more we can do for many more years. So quick statistics. We derive the number counts for based on just the MIDI, source detection, and then we find that it's pretty consistent. So here I compare it with the open squares are like from Sears MIDI data from Guang Yang's work that was recently accepted, and then also it's like compare it with the one literature. I guess from Fazio 2004, one of the earliest estimates of number counts based on Spitzer. And then comparing it with the channel 4 direct magnitude comparison, it's like beyond certain point, it's sort of source confusion and all of that comes into picture. So it's not believable, but what I show here is like all the phi sigma erect detections over this brightness range, and they're pretty consistent. So I know it's like the MIDI filter isn't exactly overlapping with the Spitzer, so there's a lot of so that's one reason why there could be sort of discrepancies in terms of like some of the disagreements in the number counts and over here as well in the direct comparisons. I just want to highlight, so using this MIDI observations, we have had a bunch of papers out. Max talked about the EOR candidates that came out earlier this week. And then there was the dust obscured galaxy that was published recently along with this source of a similar kind that was discovered in Sears. And then Erini earlier this week spoke about the dust obscured radial loud AGN. So we look forward to coming out with more science, and we kind of want to encourage the community to use. So we did release our data, the first 6 observations, 6 visits, so that's something we would want to sort of encourage people to use. So lastly, I just want to touch upon one thing that's like dear to me, like in terms of science. So the extreme emission line galaxies. So ever since the SMAX image came out in like July 2022, people were after the high redshift objects, and it just showed us that, all these high redshift objects are like the extreme emission line galaxies that people have been seeing in the nearby low redshift universe. So now we have set out on using the 277 and 444 to sort of detect cut in terms of picking up the most extreme emission line galaxies. And this is just an example. So you can see it's an oxygen 3 emitter with an equivalent width of 3,000 angstroms. Can you believe it? So I know you don't believe it. So we are after this. Some of these, we have hundreds of these. So hopefully we want to sort of follow up in cycle 3. I hope the tech is listening. So yeah, but there's tons of these objects. So yeah, it's just to go back to this image. So there are ton of these objects. I'm not trying to fool anyone here. They're littered like dust, pun intended. So yeah, so it's just amazing the kind of science we can do with Cosmos. With that, I just want to leave with the final slide. Just want to show, this is the NIRCam data which Max showed, and this is just a MIRI which I can get over with. And then the public release, you can always access it using the QR, and I can take questions.
Thank you so much. All right, questions. Oh, no. All right. Questions. Feelings, thoughts, opinion. Ah, yes, okay.
So John Debus, Space Telescope Science Institute. So as a person who finds galaxies as like a background contaminant, so I apologize, this is my trash in a way. Like looking at a random patch of sky, what is the galaxy, right? Is it the AGN? Is it something else? I'm just kind of curious, like what am I looking at when I'm looking at these background galaxies on average?
So I think most of these are like, I don't know if I can say for sure that they're of a certain kind, almost always. It's like, there can be dusty, star-forming galaxies, there can be massive quiescent galaxies. So one of the reasons why 770 was picked was to look for these rare, bright quiescent galaxies at redshift of 4 and higher. So yeah, I guess if you were to talk to Irini, she would say many of those are AGN. So yeah, I guess it's going to be a mix of things, and given the scale of like the field of view of Cosmos Web, so you will find anywhere a handful of any of those objects.
I think, any additional questions? I'm so sorry, we'll have to move to the Slack. We need to move on to our next speaker. So thank you again. Are you gonna pass this? I hate the ringing. Can we turn that off? Can we turn that off? Is it okay? Yeah. All right. Next speaker we have is Vasily, and we're going to hear about insights into the HST dark star formation from NearChem and NearSpec, or also painting the cosmos red as well. All right, take it away.
Brilliant. Can you hear me? All right, it's so nice to see such a full auditorium on this last session. I'm Vasily. I'm a postdoc at the Kaplan Institute in the Netherlands, and as Taylor just said, I'll be talking about some of our work related to red objects that we have uncovered with Webb in the last year. And I think before talking about Webb and the wonderful science that it has given us, right, it's important to mention the 30 plus amazing years of service that HST provided us with, right? And I think one of the greatest achievements, at least for me, is HST looking at lensing fields, such as this one, right, to really push the original design specifications for the instrument to its limits and detect the highest redshift galaxies. And this image on the left is actually something that myself and Gabe Brammer have re-reduced not just for the cluster fields, but for all of the other HST observations in preparation for Webb data to combine the two telescopes together and really extract as much as we can from the two facilities. Now, if we compare this image from HST to Webb, right, from the Uncover Treasury Cycle 1 survey, we see there is a very stark difference. I hope you can see that. And beyond, of course, the improved resolution and the redder wavelength coverage that Webb provides us with, you can see that one other detail stands out is Webb detects more of these multitude sort of these HST dark, HST faint red objects, right? And if we zoom into just a random part of the field, we can see how a few of these red things compared to HST start to stand out a bit more. And there are two types, more or less, that I really care about. First one is the so-called dusty HST dark or HST faint galaxies, right, which are very important for us to study since we have largely missed all of these populations with HST. They were only detected by sub-millimeter infrared facilities, right, and they seem to be contributing massively to the star formation rate density at high redshift, the high mass end, so missing them is a bit of a problem. Unfortunately, now we're finding more and more of these, and also not just finding them, but resolving them in such a beautiful level of detail where you can see spiral lumps and individual star-forming clumps sometimes. The other thing, which falls into the same color card selection, but is completely different, is the population of the little red dots, which we have heard about in a few talks this week, and they're characterized by this red color, but they're much, much more compact, and they form an entirely different population altogether. So to start off, earlier this year, we have published a paper which looks at one such example of an HST dark galaxy at redshift 2.58, which With the SED fitting, we have been able to understand that this is a star-forming disk with an AV around 4, flanked by its quiescent elliptical companion, and it appears that both galaxies are in the process of merging with each other. They're also extremely massive, around 10 to the 11, so potentially they will act as progenitors of the massive galaxies at centers of galaxy clusters in the local universe, as has been predicted, right, from all of these JWST duck works. But the other curiosity is we also get the same answer from infrared and ALMA data, right? So Able 2744 is covered by Herschel and ALMA. So if you take all of these data and perform a CD fitting again, you recover the same answer, right? The galaxy in the center is extremely dusty, and the quiescent companion is completely non-detected by ALMA, which implies to us that the star formation in this object has ceased. So using just the integrated photometry when you have such beautiful data is a bit of a loss, right? So what we've done on top of this is to take, this slice with the two galaxies and split it into spatial bins, right? To perform this adaptive binning algorithm to maximize the signal to noise per bin and split it into something like 100 bins in total. And then take each one of these bins and run them through the SED fitting again and see what we get. So what we got in the end was this beautiful map of AV dust extinction for the two galaxies, and as you can see, quite expectedly, the star-forming disk is very dust-obscured in the center and kind of peters out as you go to the outskirts, while at the same time, the quiescent galaxy appears to be largely dust-free, which is also in line with our expectations. Now, if you take those SED fitting results and try to place the spatial bins on the UVJ diagram, which is something that we use to characterize where the galaxies are star-forming and quenched, the majority of the segments that belong to the quiescent galaxy are in the quenched part of the diagram. They're on the upper left. So again, it's great to see that things make sense, even on a spatially resolved scale, right? Not just for the integrated photometry. But I believe that still, this is not nearly enough to understand JWST duck star formation. And resolved sub-millimeter observations of dust, right, with ALMA are still largely missing. So what we would like to do is to continue and push this analysis to much, much longer wavelengths. However, the current data in the field in Able 2744 lacks the required spatial resolution. Not anymore. So we've applied for some ALMA time for 33 of these JWST duck galaxies in Able, and we got the time, we got 30 hours, and what we'll do is we're targeting the spatial resolution of around 0.2 to 0.3 x-second, so not quite as good as Webb, but good enough and much better than what we had before. And our goal is to perform the full panchromatic analysis, right? To go and take the optical near-infrared data and push it to the sub-millimeter regime to really understand how the star formation rate from the infrared evolves across the entire galaxy, right? And also how the dust mass distribution looks like. All of these things are quite imperative towards a full and complete understanding of JWST duck star formation. So this is coming up in a couple of months, and looking forward to analyzing these data when they come out. The other thing, which again, as I mentioned, does fall into the same color selection cuts, but is a completely different thing, is the population of red dots, right? And initially, these were selected in the early James Webb data, and we ran ahead of ourselves a little bit, and we sort of thought that these are very, very massive galaxies, potentially something that can break our cosmological frameworks. And, can't really blame us for that, because they're everywhere, right? We see red dots in every field. This is just a beautiful image from Lucas Furtek in the Able 2744, highlighting a couple of these red dot examples. And as has been mentioned in a couple of talks yesterday, they're also in Sears, they're in Fresco, they're quite abundant, but we are still lacking, I think, a full understanding of what these objects are. So, as I've said, if we compare the red dots, just take the color cut, right, and compare the red dots to the JWST duck galaxies, they're very, very similar, right? They're red, so of course, if you blindly select these things from catalogs, you're ending up selecting two very different populations. Now, if you cut the samples by compactness, right, you're seeing a very different picture where the duck galaxies, the JWST duck galaxies, are now a completely separate population, as shown in this plot. If you go a step further and look at the photometry of the red dots, you're seeing this characteristic V or U shape, right, where it's very flat in the UV optical regime and becomes starts to ramp up almost like a power law in an infrared. Of course, if you take these data and start applying standard star-forming galaxy templates, you will fail to really reconcile with what our expectations about the universe are, right? Which, again, as I've said, leads to the stellar masses that are breaking our existing cosmological frameworks. And also, it doesn't make really sense in my head to have a galaxy with two completely separate components, one of them being dust-free, another one being dust-obscured like that. But now, if we take the reddened quasar templates and the blue quasar templates, right, the dust and obscured quasar templates, we're seeing that our answers start becoming slightly much more reasonable, right, as shown on these examples on the right. And it seems that the observations with Webb are potentially revealing an emerging population of point-like red AGN in the high redshift universe, which, if they're really AGN, can provide the link between the quasars at lower redshifts and the supermassive black hole seeds. So keeping all of these things in mind, right, it's very nice to talk about our interpretations from photometry, but let's think about physics just for 1 second. So as Dale, I think, mentioned yesterday, the physical picture that we're trying to paint here is that to explain this double component SED shape, it can either be a reddened AGN, right, combined with the unobscured, scattered light that's kind of going out at top and then being scattered into the line of sight, or a multiple stellar population fit of blue plus dusty template. Of course, still, I mean, even if the template fits do not make sense, we shouldn't discard these hypotheses because that's not what we do. But fortunately for the Abel field, we also have ALMA. And as I've mentioned, if you're not seeing anything in ALMA at 1.2 millimeter, then there's very likely a really no star formation going on, right? There is no galaxy component being present to provide this boost to the infrared data. And actually, all of the red dots that we have selected in Abel 2744 are not detected by ALMA at all, which might imply to us that indeed we're looking at AGN rather than a double component fit to a star-forming galaxy. Now, to get the real answer and to understand what's going on, I think it's worth looking at spectra. And fortunately, 1st of August, the Uncover program got the beautiful 650 plus spectra, as you can see here on the left, this nice combined spectral plot by Sedona Price. And 17 of these objects in our MSA slits were the red dots, right? Turns out that 14 of them are broadline AGN with H alpha and H beta being broadened depending on where they lie. 3 of them are brown dwarfs, which is a bit unfortunate, but also highly interesting. And the overview paper about these red dots actually came out yesterday by Jenny Green, so you should check it out. And also, in the last couple of weeks, we've also been putting out papers related to these red dot populations, which we'll discuss in the next few slides. But before I get into that, here's a few fun examples of the red dots in the field. The one on the left is the highest redshift red dot that we have observed, with the broadline AGN component being present there, which is kind of obvious even by looking at this diagnostic plot. And the thing on the right is the 22nd magnitude broadline AGN at redshift 4 and 4.5, which is absolutely mental, right? I mean, 22nd magnitude, it's crazy. So looking forward to Ivo explaining that, but what I can explain is the broadline AGN, right? So if we go to that, we detect a bunch of beautiful lines, not just H beta in the O3 doublet. We also see the auroral O3 emission. We see the different hydrogen lines, magnesium, even Lyman alpha. And if we zoom in on the interesting part of this plot, turns out that performing a double component fit to the H beta works best, and we're finding that indeed there is a significant broadening in this line around 3,500 kilometers per second. So, which unequivocally proves the existence of a broadline AGN contribution in this object. Now, if we try to place it into the context of the other objects discovered at similar redshifts, right, we're seeing that the study of these red dots provide us with a kind of a unique parameter space to understand the supermassive black hole growth and galaxy coevolution. What we're finding is, from an upper limit in the stellar mass, is that the black hole to stellar mass ratio is around 30%, which is very, very high. And it's not just us finding this, it's also work by Roberto Moellina, which finds the same kind of thing at lower redshift. And does this really mean that these black holes that we're seeing grow before the first galaxy? Or is there something else going on? Unfortunately, for now, it's really impossible to provide the answer, but we can speculate, right, and try to understand how these things form so early into the history of the universe. And on my last slide, I just want to present some of the other quasars alongside ours and kind of comparing different growth scenarios for these objects. And it seems like either the direct collapse black hole scenario accreting at Eddington rate or something that is stellar but super Eddington would be required to support the existence of such high masses in black holes so early into the history of the universe, just less than 1 billion years, right? However, both of these scenarios are quite unique, right? And they're difficult to support because one of them would require collapse of a massive pristine gas cloud, right? With very high Jeans mass, and the other a high accretion rate in a stellar mass seed over long timescales. What is clear, though, to me is that the ubiquity of the red dots and the overmassive nature, alongside the other Heise equations that we're finding, poses challenges to our models of black hole growth and black hole galaxy coevolution, which is extremely interesting, and we'll see what we'll discover in the next couple of months. And I'll just leave you with my conclusion slides. Thanks.
Great. We have time for one question. All right. I saw that hand first, unfortunately. Sorry.
Thank you so much. This is really awesome to see. So in Jenny's paper, she basically said that the UV nature of the UV continuum was unclear. And so I was wondering, what are your thoughts on that? How does your source, do you come to the same conclusion on whether we're looking at a very strange type of scattering situation for these types of things or something else?
Right. Well, for the scattering scenario, right, you don't need a lot of light to be scattered. It's around 2 to 3% of light that needs to be there to support this blue part of the SED. Also, I mean, we're not seeing anything in ALMA, right? Nothing at all. And in order to support some kind of a reasonable model of a star-forming galaxy or star-forming host galaxy underneath this AGN, we would require for this thing to be detected in ALMA. And also just in general, from the compactness alone, right, you're not seeing any host galaxy behind that quasar. So all of these things together kind of tied up, and also just performing sort of an, I didn't mention this in the talk actually, but what we've done on top of this to get the stellar mass estimate is to take the spectrum and fit it with a bunch of different templates, including red, blue quasar, and the star-forming galaxy underneath it, and then pushing it all the way to the ALMA and kind of trying to tie all of these 5 or 6 different template families together, and we still get the same result as we're getting from just purely kind of speculating on the photometry results. I think I can't say definitively whether there is no host contribution, but I'm pretty sure that there isn't, at least for this object.
Great. All right, let's thank our speaker again. Next, we have Iris, and we'll be hearing about MIRI-only sources and the MIRI Deep Imaging Survey. And I'll put 12 minutes here.
Okay, perfect. So I'm a first-year PhD student at the Cosmic Dawn Center in Denmark, and I'm going to talk about MIRI-only sources in the MIRI Deep Imaging Survey. So one way of detecting galaxy candidates, especially high redshift, is to use the dropout technique. So it consists of finding in photometric data a strong signature in the spectral energy distribution of a galaxy. It's been so the most common spectral drop that we use in this technique is the Lyman break. So in the photometric data, as you can see here, we have no detection, and then at longer wavelengths we see it. And this is kind of the spectral equivalent of that. We can see the drop of flux, and this is what we find where we spot in the photometry. So this technique has been widely used with HST, and we could detect galaxies up to redshift 11. So the very famous galaxy detected with this technique is GNZ 11. And now with James Webb, and especially NIRCam, we could detect galaxy candidates at redshift even higher than that. So another cause of a dropout in the SED can be dust. So in this work by Barufed et al., they selected a sample of galaxies that were detected in ALMA and in Spitzer, and that were HST dark or HST invisible. And these galaxies have been revealed in NIRCam data. So yeah, another cause of in the spectrum that causes a dropout in photometry can be emission lines, or rather strong emission lines sometimes mimic Lyman break in the photometry. So this has caused some degeneracy in the best fit when we fit the SED models. We often have a solution of a low redshift or redshift 5 dusty galaxy, or a high redshift Lyman break. So we can see this really nicely here in this plot at the bottom, that O3 and H alpha can cause a detection in all these bands, these NIRCam bands at wavelengths longer than 2 microns, but no detection in the bands at wavelengths lower than 2 microns. One other signature in the spectrum of a galaxy that one can think about is the Balmer break. However, there are some caveats when we use the Balmer break as a signature when we look in photometric data. One is that at 4,000 angstrom there is a Balmer break, or the D4000 break, which comes from different physical processes. And if we have photometry, we cannot disentangle these two effects. The other caveat is that strong emission lines sometimes contaminate this photometric band and can show a very strong break in the photometry, which is then overestimated. And also for high redshift galaxies, we may not expect having a strong Balmer break because it requires the stellar population to have a certain age. So recently, for the first time, there has been a sample of spectroscopic observations with James Webb of specifically targeting the Balmer break of high redshift galaxies. And they compared that to simulations. So here the black line at the simulation, the data point here is the galaxy I showed just here. So for redshift 7, it suggests that this break at 4,000 angstrom is of the strength of 1 to 1.4. And that if you go at higher redshift, this break is shallower, and also that the brighter the galaxy is, the brighter the break. So not bright galaxy have not a strong Balmer break. So can the Balmer break cause a dropout in photometric data? Probably not at high redshift. So in this work I'm presenting you, I'm looking for galaxies that were HST dark and NIRCam dark, and only detected in MIRI. And this is possible in the MIRI Deep Imaging Survey. So the MIRI Deep Imaging Survey of MIDIS is the deepest MIRI image to date, with a 50 hours exposure in one single MIRI pointing at 5.6 micron. It's data taken with the MIRI, the European MIRI GTO team. It's part of the HUDF. And so I've been looking for sources that are only in this image and not detected at shorter wavelengths than 5 microns. So to find these sources, I compiled HST and NIRCam public data. So I have in total a set of 24 photometric bands from 0.4 micron to 5.6 micron. And I look for sources that are only in the 5.6 image. So if you just think about what these sources can be, what is the nature, so they could be a line emitter at redshift about 10. If you look at this spectrum, we can imagine that if this H-beta O3 line falls at 5.6 micron, it can cause a dropout in 5.6 and it not being detected in any other band. It could also be a low mass dusty galaxy. So this is the, as you can see here, it's the galaxy that Vasily showed just before. If we imagine the similar object can cause a detection in 5.6 but not in the other band. So these are the depths in all the bands. It could also be eventually a Balmer break at a redshift 13. But yeah, as I discussed before, it's maybe the less likely solution. And if you think about the Lyman break, it would make this galaxy be at a redshift 40. So this is not really an option we want to consider. So to detect this MIRI-only candidate, I optimized the source detection in MIRI using Sextractor. And then I kept the sources that have a signal-to-noise ratio greater than 2.5 in MIRI and lower than 2.5 in all the other bands. And then I looked at them individually in cutouts. So this is kind of tricky to determine which one are good candidates or not, because some look quite convincing, but some are also like effects here in the PSF of MIRI, or some it's difficult to say if it's a source or if it belongs to another neighboring source. So I kept a very conservative sample, and I found 6 MIRI-only candidates, such as here. And there is one in particular, my favorite MIRI-only candidate. I'd like to show you in all the 24 bands. And I'd like to drag your attention to looking at the 5.6 and then the NIRCam 366 or 444. So we can see these 3 objects around that are in the NIRCam data and also in HST. But the source here in the middle, this MIRI-only candidate, is not visible in any other band. So the question we can ask now is, are these galaxy dusties? So to answer this question, I went to the ALMA archive. And since this image is part of HUDF, we will have also very deep ALMA coverage of this part of the sky. And I looked at how these galaxies look in ALMA. So there is no strong detection or no clear detection in the ALMA data. However, this favorite MIRI-only candidate might have tentative detection, but slightly offset from the center of the source in MIRI. But if this galaxy turns out to be also detected in ALMA, it could be quite exciting to have a galaxy that is detected in MIRI and in ALMA only. But here also, we should keep in mind that if these galaxies are low-mass galaxies, they might be below the limit of what ALMA can detect. So the fact that we don't see them in ALMA doesn't mean that they're not, they may be just below the limit of what can be detected. So the last thing we did is we fitted LCD feeding codes on these galaxies. We tried with easy bagpipes. So just to remind you that we fit 23 upper limits and one shallow detection in MIRI. So the results are not very robust. But the good thing is that they seem to converge to similar solution, meaning rather a solution at low redshift 3 or 5, and low mass galaxy, so about 10 to the 7 solar masses. These galaxies are probably not a Lyman, or they're definitely not a Lyman break galaxy. It's likely not a Balmer break, and probably they're like low mass galaxies that are dusty, and that's why we don't see them in NIRCam and HST. So just to summarize, so for the first time, we've looked at dropouts at 5 microns, so HST, NIRCam dark galaxies, and this is possible only in, for now at least, in this image from the MIRI GTO team, and we find 6 MIRI-only candidates, and that this LCD fitting suggests low mass galaxies, and so we need more observations for these sources. But then, yeah, we're a bit limited with the data because for this was 50 hours with one single MIRI pointing, so we would need a lot of hours to get a spectrum or even deeper ALMA data. So I'd like to thank the MIRI GTO team and the Cosmic Dawn Center. Thank you.
All right, we have time for a few questions. Questions in the room or on blue jeans? Yes, of course, you're at the other end of the room.
So, yeah, for the LCD fitting, can you combine the optical data with ALMA and actually see what you get from that upper limit in ALMA and maybe try to predict the stuff formation rate?
Yeah, I haven't done it yet, but yeah, it's something we were gonna try. Yeah.
What's the depth of the NIRCam imaging compared to MIRI?
It's a little deeper. I think the JADE is like 30 or 30.1, and the MIRI is 29.3. Yeah.
Cool. Okay, one more question.
Since it's a relatively small field, if you assume it's like really crazy dust obscured star formation in order to not get a detection in NIRCam, what would be the chances of you even detecting that kind of source in JADES? Would you be expecting that you would need the wider field surveys to find something not detected in NIRCam but in MIRI? The rarer objects, or have you looked at it in terms of space densities and predictions for JADES?
Yeah, actually, I don't know.
Cool. Any final questions? All right, let's thank our speaker again. All right, next speaker. Yes, hello.
Can you hear me in the back? Okay, cool. Okay, good.
All right, our next speaker is Yechi, and we'll be hearing about statistics for galaxy outflows at redshift 6 to 9 identified with NIRCam and NIRSpec. I'll put 12 minutes there.
Okay, great. Thank you. Okay, second last talk. You guys are still okay? Yeah, thanks for sticking around. I'll try to make this real quick, okay? So yeah, I'm Yechi Zhang from the University of Tokyo, and today I'm going to talk about the outflows in James Webb. And just a spoiler alert, I'm just accidentally in this section. So the objects I'm going to talk about are not necessarily dusty, actually. So yeah, let's get started. So yeah, we know that outflows has been extensively studied in the local and nearby universe because they're quite important in revealing the baryonic cycles in the galaxy evolution. And while with the James Webb, previously maybe we can look at these, spatial extension by putting a narrowband filter on them. As we can see the extended H alpha in the famous M82, or we can look at the spectra, looking for the broke components of the ionization line, or we can do both with IFU. And while going to the high redshift, finally with James Webb, we're reaching these. We're reaching the very high redshift of these galaxies. And while there are many programs studying the outflows and targeting these outflows, for example, Fujimoto 2022 observed with ALMA looking for these redshift 8 galaxies, found offsetted carbon-2, and there are also other proposals targeting those AGNs. But so we're just wondering, what's the big picture of outflows in these very high very high Z galaxy newly identified with James Webb. So what they are driven by, or like how frequent are they in the galaxies? So that's the purpose of our study, and just trying to systematically investigating the outflow in these new JWST galaxies with the both imaging and the spectroscopy. And for the imaging data we use is just the public James Webb NIRCam images of these 3 surveys, shears and cover. And ERO, again, a big thanks to the teams for making it available for the whole community about this amazing data. And well, in this field, we also have the spectroscopy of the near spec with different with ERO shears and the glass in the uncovered fields with different spectral resolution. And actually, Nakajima et al. 2023 compiled all these data and identified a 185 star-forming galaxy at redshift 4 to 10. And while based on these data, we do these will serve as our parent sample. And remember that they're all spectroscopically confirmed with the NIRCam. And we first start with the imaging, and what we use is the broadband access. For example, for redshift 6-ish galaxy, we have the O3 and H beta entering the F356 band, and in the adjacent bluer band, we only have this stellar continuum optical, rest frame optical. So if we do this subtraction on the PSF matched image, we'll end up with a pure emission line image, presumably without the contamination from the stellar continuum. And we do this analysis with 2 different filter sets on 2 different wavelengths range. And finally, we end up with 61 galaxy within this redshift and with the coverage of near spec. And if you look at them, they are basically typical main sequence galaxy at the very high Z. Okay. And then we first look at the spatial extension of these objects. So we did it in this following way. First, we look at the emission line image to make sure they have high enough SN. And then we compare the effective radius of the emission line image and the continuum one to make sure that the emission line is more extended if you look at this red contour overlaid on this optical one. And finally, we check the visually inspect the radial profiles to make sure what we're looking at are not artifacts or something. So in this way, we ended up with 5 galaxies here. If you take a look at them here, they look like this. They're all quite extended in the spatially extended in emission lines. Okay, and then we we'll go back to the spectrum to check the near spec, and we actually focusing on the O3 doublets, and we find 1 object with the broad components indicating the ongoing outflow. And in 2 of them, we didn't find anything. It's a single Gaussian fit is preferred. And another 2 is actually taken with prism, in which we don't have enough spectral resolution to do this 2-component fitting. So that's the story about the spatial extension. And then we move on to the spectrum and for the broad line. So again, we go back to the sample and fitting all the O3 doublets. And we ended up with 5 objects in which the O3 doublets is preferred by a 2-component Gaussian fit, including a broad component. It's okay. And again, among 5 of them, only 1 of them are spatially extended. So that would be quite interesting thing. And so we have looked at these objects with spectrum and imaging, and now we go back to get some calculation on the number. So again, we want to make sure that all these objects we're looking at have a high enough SN, so that any potential spatial extension and the broad line components should be recovered if they are there. So, if you look at the spectrum data, so this gives a number of 5 out of 17, which is around 30% of the objects with the broad emission line. And similar story for the spatial extension, there are around 16% of galaxies are spatially extended in the O3 emission line. And if we look at this top right area, so again, the things we mentioned is the discrepancy between the broad line and the spatial extension, because we assume they both should trace outflow, but actually there is a little difference between these two samples. And while we we want to know what causes such a discrepancy, and the first possibility is just the viewing angle, assuming a biconical outflow. And if you're looking from this outflow interaction, we see broad line because we see the velocity difference. And well, from this number fraction, we can actually calculate the opening angle of this biconical outflow, while using the fraction that we can see with the broad line, and which yields to a pretty large opening of 73 degrees. And if we look at from the perpendicular to this outflow, we should see the spatial extension. And if we see from somewhere in between, we'll see both. And well, this kind of scenario is also mentioned in this JWST team's paper, Caniani et al. 2023, who did this with by only looking at the spectral data. But what we found out is by also looking at the imaging, by the spatial information, there's one problem was that the open angle seems to be too large. So that any spatial extension should also observe the broad line in this situation. So well, this is the problem with this scenario. And so we come up with another possibility. Is about the gas cycle in the high Z galaxy in the periodic star-forming history. So for example, if we first start with in the early outflow phase, where the outflow just happened inside the star-forming region. So you can see the broad line, but the ionized gas are not blown into the IGM yet, CGM or IGM yet. Then as time goes, the ionized shell keeps expanding, and you can see the spatial extension. And then in the next phase, then the outflow halted, while this ionized gas shell still remains in the CGM or IGM, so that you can still see the spatial extension. And finally, we come back to this, we come back to the original and start this whole cycle again. And this kind of a scenario are more common in high redshift because of the very high merger rates and the compact nature of galaxies. So this is the second possibility. Well, in fact, we don't know which one of them are true, and probably maybe the mixture of both. So maybe the future observation, IFU, or both ALMA will tell you more about that. So yes, that's the possible scenario. And we next investigate the strength of the outflow on those broadline objects. And well, if we compare this maximum outflow velocity calculated from the nearest back and compare with the escape velocity of the dark matter halo of this galaxy, and we found this ratio is below unity for our sample, which indicates that the outflow happening here are not strong enough to eject the gas away from the dark matter halo, which kind of supports the previous gas cycle scenario because they are finally coming back to the star-forming region. Okay. And finally, it's the possible origin of what drives such kind of outflow. So we, with the near-spec data, we checked several possibilities. So they can both be from star-forming galaxies or AGN. So we first checked the AGN, and we didn't find any broad components in the Balmer lines. So they are not the broadline AGNs. And then with the available data, we checked this line diagnostics. And well, although it says unlikely here, but well, people have been talking about it in previous days, things start to get complicated for these diagnostics. So we actually don't know. We cannot say the AGN doesn't exist. And finally, if we look at the number fraction that I just mentioned and compare them with the low Z counterpart, we can see a significant, we can see increase in both the number fraction of spatially extended objects and in the broadline fraction. So indicates that either due to AGN or star-forming activities, these outflow might be driven by the higher merger rates that are happening at the very high redshift. So I will just leave my summary here, and I'm happy to take any questions. Thank you.
All right, we have some time for some questions in the room or on Blue Jeans.
to do some quantitative science with these types of observations, it would be nice to know what the mass outflow rates are. I wonder if you have any even rough estimates of what those might be.
Well, I think, yes, that's what we're doing now. I don't have the exact number now, but that's some of the things that we're still checking at. But you're right. Well, we can make a rough check with the currently available data with some assumption, or we can confirm it with the IFU observations. But yes, you're right, that's quite important.
I have an additional question. So ideally, if you could get more data, which is like the observer's dream, what data would you like to further explore these kinds of outflows?
Well, we
With
can.
JWST maybe.
Yes. If looking at the JWST, we can look them with IFU. But well, the seamless noise will always be a problem. But assume we get enough data of it.
Infinite IFU.
Yes, we can do this kind of a profile fitting to see like the direction and the morphology of this outflowing gas to see what are we really looking at this. Is this due to the kind of a duty cycle and the on-off phase of outflow, or galaxy of outflow, and we're just looking at from different direction, and also the strains. Yeah.
That'd be so cool. Question online, go for it.
Yeah, this is from Jung-hee Ro, who asks, is there evidence of shock as outflows?
Well, yes, that's a very good question, and maybe. Well, to be honest, I don't know. Yeah, we still need to look at that. Yeah. But yes, outflow might be possible. Shock, yeah.
Great. All right, let's thank our speaker again. And
Thank you.
Okay. Perfect. Yeah, exactly. Perfect.
And it should work.
Perfect.
all right, our final speaker, no pressure, of this entire conference is David, who will be talking about uncovering the mid-infrared emission of quiescent galaxies with JWST. All right, take it
All
away.
right, thank you. So first of all, congratulations on making it till the end of the conference. You are now one of the privileged few who will get to see my talk. But jokes aside, my name is David Blanca-Sese, and I'm here to speak to you about uncovering the mid-infrared emission of quiescent galaxies with JWST. Okay, so brief introduction. When we are speaking about star formation, we resort to differentiating galaxies between star forming and quiescent galaxies, with the latter being characterized by very low levels of star formation and therefore old stellar populations and redder colors. The main question that we've been asking ourselves as a community is what drives quenching? So this is what suppresses star formations in these systems. In order to do this, we have widely studied quiescent galaxies in the local universe where their numbers are greater and where they are easier to observe. However, in latter times, what we have tried to do is to extend these studies into the high redshift universe. Why? Because studying quiescent galaxies at high redshift universe inherently places us closer to the quenching event. So when it comes to high redshift quiescent galaxy studies, I have divided them into three areas. First one is the UV optical near infrared, where we can study the stellar content of quiescent galaxies, and we've been able to find the size-mass relation of these kind of galaxies and also the location in the star formation and stellar mass plane. Now, when it comes to the far infrared and the submillimeter regime, so this is the ISM budget that quiescent galaxies have, we find a picture in which measurements are not pointing towards a conclusive answer. So we have some stacking ensembles here in blue, we have some lens systems in white, and some spectroscopic observations in gray. So in this conundrum, I tried to put my grain of sand, and I did a high-resolution ALMA stack, and I found out that apparently galaxies quench with measurable amounts of gas within them. And this conundrum is just a result of that each method that you utilize inherently selects different systems according to their stellar mass.
Now, here you can see the mid-infrared studies. There are none until now. Why is this? Because before, our mid-infrared observing facility was Spitzer, which, even if it was a great facility, it wasn't powerful enough to observe the mid-infrared emission of quiescent galaxies. However, now this has changed with JWST, with NIRCam, but most importantly with MIDI, which is one of the best mid-infrared observing facility that we've had so far. So my work has been to use the deep MIDI photometry in the SMAC 0723 cluster field to extend the local mid-infrared studies of quiescent galaxies beyond the local universe. And I need to stress, depending on what regime you're looking at, extending to higher redshift might mean something different. In the stellar regime, by extending to high redshift, we are finding systems at redshift 4.7 or even mini-quenched galaxies at redshift 7, whereas in the far infrared, we are now pushing the boundaries to redshift 3. However, as you will see, when we extend the mid-infrared regime, these numbers are not that great. Why do we want to study the mid-infrared regime? Well, because the mid-infrared is dominated by warm dust and possible emission line features from PAHs. This is the mid-infrared, regulates the ISM, and by regulating the ISM, it regulates the condition for star formation, and therefore quenching. So the data I've used in the SMAC cluster field is the rich ancillary HST photometry that was present, the new NIRCam and NIRIS photometry, and most importantly, the deep MIDI photometry that ranges from 7 to 18 microns. In this field, I made a selection of quiescent galaxies with a UVJ color diagram, which is a very powerful tool, especially in this low redshift regime from 0 to 2. I also made a stellar mass cut, and I made an individual inspection of the cutouts in order to get rid of any possible artifacts. This resulted in a sample of 63 quiescent galaxies, which I narrowed down to 55 by getting rid of some dusty star-forming contaminants. You can see the position in the UVJ color diagram of this final sample of 55 quiescent galaxies here. And here you can see the redshift and stellar mass plane. The most important thing you must look at here is how most of the quiescent galaxies are clustered around the cluster redshift. This is 0.035, which is something not unexpected, of course. And then we have 3 outliers at higher redshift. So this is the highest redshift we can go in the mid-infrared. And for this reason, I've divided, for the next part of the talk, this sample in 2 subsamples, the low redshift one and the high redshift one containing these 3 outliers. In order to model the mid-infrared regime when it comes to SED fitting, I have used the widely known drain and lead dust models. But in addition to that, I've taken the dust component from an empirical template from this work by Paspaleris et al. In addition to this dust component of this model, I have also modeled the stellar emission with a black body at a temperature of 5,000 Kelvin. And you can see the stellar component as a dashed green line or blue line here. Why do we do this? Because the drain and lead models were first intended to model the mid-infrared regime of star-forming galaxies. So we believe that it might be the case that these drain and lead models are not good enough to capture the low amounts of dust that we believe are present in these quiescent galaxies. These are the results. So out of the 55 quiescent galaxies, we find that 9 do not require an additional dust component, so they do not have any signatures of dust within them, but the vast majority of the sample, this is 46, do require a dust component. So this is telling us that beyond the local universe at redshift 0.3, which is a good 5 gigayears in the past, dust was still present in quiescent galaxies. More information can be extracted, though, if we look at the global properties of the sample. So here on the top, what you can see is the SED of my quiescent galaxy sample as red dots. You can see in the background as gray dots the star-forming galaxies SEDs, and then in blue you can see the median best SED fit. So you can extract 2 main conclusions from here. One is that, as we knew, the SEDs of quiescent and star-forming galaxies are different in the UV, optical, and infrared, but also they are very, very different in the mid-infrared, and this we didn't know until now. The second one is that this difference grows a lot larger when we progress in redshift. Now, if we look at the bottom panel, here we have, again, the SEDs of the low redshift quiescent galaxy subsample. And here in black, you can see the best fit median SED. So again, here we can extract that. You can see a large scatter appears in the mid-infrared photometry as we progress in redshift. And what this is telling us at first sight is that the dust that we have found that is present in these quiescent galaxies has a varying strength from source to source. However, there's another possible scenario that we must consider. And this is the one in which this scatter is created by the emission line features from PAHs, or polycyclic aromatic hydrocarbons, in case I didn't say it before. Because the emission line features fall exactly where our photometry lies. So it's a good scenario that we must consider. If this scatter is in fact driven by the intensity of the pH features, then what we see is a great enhancement of the 11.3 micron feature against the 7.7 micron feature. Not surprisingly, this same behavior has already been observed for local ellipticals in the works of Bregman et al., for example, where you can see here that the 11.3 is much greater enhanced than the 7.7, or in Kaneda et al. Here. The interesting thing is that for star-forming galaxies, this intensity ratio is completely inverted. So why is this ratio this way for quiescent galaxies? Well, this is mainly attributed to a predominance of neutral to ionized PAHs in the ISM, which can be traced back to softer radiation fields. So what we want to do is we want to make a very, very rough, because this is photometry, quantitative estimate of the ratio. And we can translate this ratio into a measurement of the hardness of the radiation field. And we find numbers that are consistent with a very, very soft radiation field, which are in turn characteristic of evolved stellar populations and quiescent galaxies. So in case this is driven by PAH features, it seems that everything falls into place. Lastly, this provides us an unprecedented opportunity to take the analysis we've made from the UV to the mid-infrared and link it to previous analysis in the far infrared. So I took my UV to mid-infrared best SED fit model, and I conjoined it with a previously created far infrared quiescent galaxy SED model by Magdis et al. By doing that, we obtained something like this, a panchromatic view of a quiescent galaxy SED. In order to build it, I normalized my UV to mid-infrared SED model to a stellar mass of 10 to the 10, and I scaled the far infrared quiescent galaxy SED model down to a level where I can match it with the other model. By doing this, I'm inherently scaling the dust content. So what we find is a dust mass that, when you translate it to a dust fraction, it has a dust fraction content that is exactly what we expect of quiescent galaxies at this exact redshift. So this model it is consistent with all of the observations we've made so far, both in the UV, near-infrared, mid-infrared, and also far infrared. Here you can see my summary slide. So JWST has opened the window to mid-infrared studies, not only of quiescent galaxies, but for the entirety of the galaxy population. We have confirmed the detection of dust with various strengths in a sample of quiescent galaxies from redshift 0.2 to 0.7. So this is the highest redshift we can go with JWST, at least so far. The scatter observed in the mid-infrared photometry is also consistent with emission from PAHs, which show a similar behavior to that observed in local ellipticals. And finally, we have now provided the community with a panchromatic quiescent SED model from UV to radio that is consistent with previous predictions of the ISM budget of quiescent galaxies. Okay, thank you.
Awesome, thank you. Questions for David?
Hi, Adam Smersina from the University of Washington. So you used the Drain and Lee models, right, to fit the infrared SEDs. Do you get out any estimate of the luminosity of pause relative to the total non-stellar infrared emission?
So the thing is, I didn't go on my SED fitting methodology because I didn't have the time. But what we did is we made we made like a process for the SED fitting. First, we tried to fit with the Drain and Lee models. And in case the model wasn't able to capture the low amounts of dust present in the galaxies, then we resorted to the dust component plus black body emission. And only 2 out of the 55 were able to be fitted with the Drain and Lee models. So I'm afraid no, we didn't get to capture that. Also, take into account, you only have 4 points in the mid-infrared, so it's very hard to constrain any PAH characteristics.
I think I saw a question in the back. Was that right? Oh, here. In the middle. All right. We got this. Can you please pass this back?
Yeah, sorry about that. I was wondering if you could use the ancillary data at shorter wavelengths to try and measure stellar ages. I know it gets complicated to measure ages of quiescent galaxies, but to see if that has any correlation with your the variation you're seeing in the mid-IR.
Yeah, I think it could be done because in the UV near infrared, the data is very, very rich, but unfortunately I haven't done it so far.
All right, any questions on blue jeans? Okay, well, thank you so much. All right, I believe we have some closing remarks, and then we will let y'all free.
So I'm mostly going to thank people. I want to start out by thanking the Science Organizing Committee, Jayan, and the other co-chairs for having done, I think, a fantastic job. I deeply enjoyed all the sessions that I had a chance to listen to. I want to thank participants, the speakers, the session chairs, and the virtual overseers that allowed us to have a mixed, a hybrid meeting, and contributed to the success, I think. We had not planned a local organizing committee, which we might argue might have been a little oversight. So I want to thank particularly Chris Evans and Neil Reed, who filled in and jumped in whenever it was needed to ensure that things would flow. And we have shy people, I think, that were supposed to show up here, but are not. So I'd like to thank the AV team, Thomas, Gary, and Kevin. And let's see, let's give, yeah, if maybe it was a mistake to warn them that I wanted to do this, because they managed to hide better than
My coworkers are planning other things in the building, but they're on their way.
So should we wait for them, or? We have already thanked everyone. So I'd like to thank Sherita, Shemaya, Melody, and Holly, who provided support at the registration desk and throughout the conference. So thanks to all of you. And maybe, 5 years from now, we could have another one.